So what, heat treatment today?
I think so. Why you ask me all the hard questions? Just give it a couple of minutes. We're missing, I think, Riley. I think. You know, these computers, I think they confuse me more and more all the time. And at NAIT, usually in the summertime, we're off. And then NAIT IT comes in and they change our programs on our computers, but they don't tell us, for one, and they don't give us any training, for two. So then you'll come in September and you try and figure things out, and you figure everything's good. You go into the classroom and nothing's the same, and so you got to figure it out as you go. And I was trying to work on a document the other day, and I sent it off by email or whatever, and people that get it say, "Oh, geez, we can't read that. Open that document, and can you put it in another format?" Well, then I go back in the computer. No, you can't put it in another format. This doesn't. It seems computers are getting more and more complicated, especially when it comes to me. I'm not very smart when it comes to these damn things. Just frustrates me. All right, 28 people. I'll do my attendance and let's get this show on the road. All right, so this module on heat treatment. Why is it important to learn this skill? Heat treatment before welding or preheating or after welding or post-heating or post-weld heat treatment is mainly done to maintain or enhance the mechanical properties of the material. You must know what these heat treatments are and understand the effects each has on the mechanical properties of carbon steels. You'll then understand why welding procedures often include preheat, post-heat, and post-weld heat treatments, and why some steels are manufactured with different heat treatments. So our outcome will be to identify the effects of heat treatment on carbon steels. So let's just move forward. Alrighty. So our objectives are define heat affected zones in metals. We'll be talking about that. Explain the difference between heat and temperature. Explain 3 formats of heat transfer. Who's doing your math? Barry?
Yep.
Yep.
Yeah.
Okay, cool. I was wondering if there's Paulo, because Paulo has all these fancy gadgets, and one of them is about induction heating and things like that. It's actually pretty cool, but I have a video that is quite similar to Paulo's demo. Describe the effects of expansion and contraction. So I think in previous modules, you guys talked about expansion and contraction. Describe the purpose and effects of preheat and post-heat. Describe the practices of heat treatment. Explain the principle of temperature indicating devices. So when we were doing that W47.1, I had the paint crayon or paint marker that I was putting on the metal to check for the temperature. And there's different devices for checking for temperature indicating. So the heat affected zone, what is that? It's the area on both sides of a weld directly adjacent to where the weld metal mixes with the parent metal and stretches away from the weld until the grain structure of the parent metal has been unaffected by the heat of welding. So right adjacent to that weld, or the toes of that weld, that's where the heat affected zone begins, and then it works its way out until it doesn't affect the grain structure. So how the joint is welded greatly affects the width and the metallurgical effects of the heat affected zone. So factors to consider before developing a welding procedure is the welding process that you're going to use, the type and size of the filler metal, the current settings, travel speed and number of passes, thickness of material, type of material, carbon content of the material, amount of preheat, and what the ambient temperature is. So the heat affected zone grain structures for single and multi-pass welds. So each pass in a multi-pass weld refines the grain structure of the previous pass and the parent metal, resulting in a finer grain structure and a stronger weld. So let me just read this here. Yeah, it just says here the figure 1 illustrates a single pass weld showing the weld metal with a typical columnar grain pattern to the left. The unaffected base material appears to the right. The heat affected zone appears in the central portion, and it consists of these areas. So we have the solid liquid transition zone, which is right in here. The grain growth structure, which is in this portion here. The recrystallized zone, and then the partially transformed zone. So in the second one, because it's a multi-pass weld, everything changes. So all these grain structure gets finer and smooths out as it goes through. So figure two illustrates a multi-pass weld and shows several differences in the grain structure of the weld metal and the heat affected zone. Each pass that is applied in a multi-pass weld refines the grain structure of the previous pass and the grain structure of the parent metal that experienced growth when the previous pass was applied. The end result with a multi-pass weld is a finer grain structure in the weld and in the heat affected zone. So as a general rule, a finer grain structure makes for a stronger weld. But that being said, when you may get a stronger weld, but you may get more distortion. And it talks about achieving an acceptable heat affected zone. So one of the most critical areas of the weld zone and must be controlled to maintain the mechanical properties. So the first thing to consider is the service requirements. Is it a static load or a dynamic load? Static load is a load that doesn't move. A dynamic load is a load that continually changes and moves. So a finer grain structure provides higher tensile and yield strengths. Too fine a grain structure may result in a hard, brittle, martensitic structure, which is prone to cracking. And that's just extensive mechanical testing has been done to prove the acceptability of various welding techniques and welding procedures. By using proven welding techniques and following recommended welding procedures closely, you can be assured that your welds will meet the quality requirements, including an acceptable heat affected zone. So when we go in there and we give you a demo, we show you several things. We show you the proper fit up, and we show you how to get yourself comfortable and position yourselves. We turn around and you guys are doing something different. So just like this says, the methods we're showing you, we know work. I think I got a guy setting up camp right outside my office across the street. Okay, number two, or objective two, temperature. So it says explain the difference between heat and temperature. So what is temperature? It's the degree or intensity of heat and is expressed in degrees Fahrenheit or degrees Celsius. So there's just it says the terms temperature and heat are commonly used loosely and often interchanged as though they have the same meaning. However, this is not true. So now we know what temperature is. We're going to find out what heat means. What is heat? It's a volume or quantity and is measured in British thermal units or BTUs or joules. So just before we move on, it says a campfire produces various volumes of heat at a specific temperature, and depending on the size of the fire. And I've talked about that when I talk about setting the flame on your torch. We have the three different uh, temperatures on that little blue cone, depending on how much acetylene you got or how much oxygen you got. So you got your carburizing flame, which your flame temperature will change at the end of that blue cone, depending on how much acetylene you got and how long your feather is. Then you have your neutral cone, which is, I think it's 5,800 degrees at the end of that little cone. And then you have your oxidizing flame, which is about 6,300 degrees, and it's rich in oxygen. So the temperature is changing. And so right at the end of that little blue cone is where that temperature is. But it doesn't matter whether I got a flame that's 10 inches long or a flame that's 20 inches long. The only difference is the amount of heat that flame's giving off, but still at the end of that little blue cone, the temperature is the same. So it doesn't matter, it got a bigger flame, it's going to give off more heat, but the temperature at the end of that cone is the same. And I always that campfire one is a pretty good one. The more logs you put in that fire, the more heat you're going to get. But overall temperature would be the same. So, selecting a fuel gas based on heat and temperature. I don't know if we're there yet. So when you select any fuel gas for heating, cutting, or welding, heat and temperature must be considered. So they're giving you a little chart here. Table 1 and Table 2 provide a comparison of heat values and temperature values for common fuel gases. Table 1 shows the heat values of the gases. So we have acetylene, propane, and natural gas. So the BTUs, or the heat given off. Acetylene has the 1,470 BTUs. Propane is obviously higher, so because it gives off more heat, it would be better for heating purposes than, let's say, acetylene or natural gas, which is only 1,000 BTUs. So it says in comparing these values in these tables, you can see that although the flame temperature for acetylene is the highest, the heat value is quite low. So when you look at your flame values, you have 5,600 for a neutral flame, and you had 4,580 for propane and 46 for natural gas. These two would be good for heating purposes, but acetylene wouldn't be as good because of the heat value. This would be better for welding than these two. Not saying you couldn't do it with these two, but it's going to take longer because it takes longer to heat that metal up and bring it to its kindling temperature. So if this makes acetylene good choice for welding and cutting, where an intense temperature and concentrated heat are beneficial, propane, on the other hand, has a very high heat value, but with reduced flame temperature. This makes it a valuable fuel for general heating purposes. And you can change the amount of heat per unit of time through manipulation of the torch valves by using different size of heating tips. And this is true for all fuel gases. You cannot, however, change the temperature of a neutral flame because this temperature is governed by the chemical reaction that causes combustion. Now, heat transfer, objective 3. So it says, explain the 3 forms of heat transfer. So control of heat input is very important to a correctly executed weld. 3 forms of heat transfer: radiation, convection, and conduction. Do we got a chart here? I don't know. We do. So radiation. It's radiation is heat that travels on light waves, such as ultraviolet and infrared rays from the sun or from the welding arc. Sorry, got a little something going on there. For example, when you hold your hand over a heated object, you can feel the heat radiating from the object. Same thing with those rays. If you don't cover up your bare skin, those rays are going to radiate to your skin and burn you. Then we have convection. And convection is the transfer of heat from one body to another. So when you place your hand above a heated object, the heat is transferred to your hand by means of convection. And the ability of a material to transfer heat to surrounding materials may affect welding. And the next one is induction, and it's the transfer of heat within a body, and the rate at which a material can transfer heat within itself is known as thermal conductivity rate. And the thermal conductivity rate varies greatly in different metals and is an important factor in determining welding heat input. So the heat input, or the thermal conductivity of carbon steel and aluminum, are quite different. So where your heat doesn't move away from your welding zone on carbon steel, it moves away quickly in aluminum. So for aluminum, you might have to have more heat input in order to make a successful weld. So they're just showing you the comparison of the thermal conductivity rates of some common metals. So copper, there's your heat, and it transfers away in copper the quickest, then aluminum, brass, steel. The stainless steel is very slow. Sorry, people. Got me a little bit of a frog in the throat. So what does it say here? When welding copper, brass, or aluminum, you require much greater heat input than is required for the same mass of steel. This is because the metals conduct heat away from the weld area much more quickly than the steel. Figure 6 compares the effect of thermal conductivity between aluminum and mild steel on a set of welding coupons. For the aluminum, you can see the heat input. Here's your joint, and it's traveling away a little quicker. So you probably have to crank up the heat a bit more than you would in the steel because the heat stays more localized. And then sometimes alloy additions can have a marked effect on the thermal conductivity rate. For example, austenitic stainless steel has significantly lower thermal conductivity rate than mild steel because the heat builds up around the weld faster on stainless than on steel. You must have be more careful of heat input on the stainless steel welds. So you can take advantage of the effects of high rates of thermal conductivity by using highly conductive materials as chill strips or heat sinks when welding on thin sheet steel. And then it says they support the work and draw the heat away from the weld to prevent overheating. This provides better control of heat input and weld puddle. And well, in welding metals that are high in thermal conductivity, you may have to use extensive preheat or insulate the metal away from the joint edges in order to overcome the heat loss. Now, objective 4, expansion and contraction from welding. So like I said, we've already covered this in other modules, um, but it's good to rehash it. So expansion means there's an increase in size or swelling, which is usually associated with a rise in temperature. The three types of expansion encountered are solid expansion, transitional expansion, and fluid expansion. So solid expansion, I don't know if we got it all. So as the metal cools, it shrinks, and this is known as contraction. And it just talks about the solid expansion occurs when the metal is in a solid condition, has not reached its transition temperature. The transition temperature for steel is 1333 degrees Fahrenheit. Then transition expansion takes place above the transition temperature. Steel will transition or change from one crystalline structure or form to another. During this transition, steel remains in a solid state. And then fluid expansion occurs when in molten metal. So as a metal cools, it contracts or shrinks, and contraction is the opposite of expansion. So they talk about free expansion and contraction. So what is that? So you guys talked about this in a previous model. You have a solid block of steel. You heat it all up evenly. It expands in all directions. And if you allow it to cool down, it will return to its original size and shape. So it just shows you how that all works. Then they talk about the restrained expansion and contraction. So what is that? You guys have that vise that's holding that bar. So you heat it up, and as it heats up, it can't go lengthways, but it can go in the other directions. So this is the bar before heating. The red line is the bar while heating, and then the blue is the bar when you let it cool. Because it expanded in the other directions, when you let it cools down in all directions, so you end up with a shorter, fatter bar. Now they talk about using expansion and contraction. Yeah, and I guess if I go back here, just the one thing I did, it doesn't say. During cooling, however, the bar is free to contract in all directions. Contraction takes place in direct relationship to the bar's hot dimensions. The result is the bar is now shorter but thicker, and the shortened and thickened condition is called dimensional upset. Now we talk about this, if you're using. Before I say that, uh, okay, fusing expansion and contraction. Doesn't have anything in the PowerPoint. So the effects of expansion and contraction can work for you in several ways. If you know beforehand that a weld is going to pull the parts out of alignment, then you can preset the parts so that the welding pulls the parts into alignment. An example where a spoke on a pulley is broken is shown in figure 9. Heating the rim on both sides of the broken spoke, 9A and 9B, causes the brake to expand open. 9C, you must keep the preheated areas hot while the brake is welded and then allow the unit to cool. This procedure results in very low residual stresses. So by heating this, it expands this, you weld it up, allow the 3 spots to cool, and it takes off that restraint. And the next one they're showing here is the wheel is broke, so they're heating up the hub. Another example where a break in the rim has occurred is represented in figure 10. Heating the hub of the pulley causes the brake to expand open for welding, and the part has little, if any, residual stress on cooling. And then many times I've used this using a dimensional upset. I used to. Did I talk to this module with you guys when we were talking about all that? Or I have to ask because I do it so many times. I used to do work on tractor trailers, and the dust shields would break off, and the studs would be broken off into the mount for the dust shields. So I used to weld a nut on here, and by welding that nut, it would cause this because it couldn't expand this way, it'd expand this way, but then it would contract in all directions just like this, and then I could thread that out. So I used to do it with something like this. I had a really tiny, because it was only a 5/16 nut, I had a really small pair of vice grips, and that's all I used them for, because sometimes you get a stray arc on that vice grip because it's so small. And then I'd put that electrode in there and zap it on there, and it would remove that stud. And I did that on manifold bolts that broke off. I did it on transmission broke off. The studs broke off on a transmission at the back of the engine. And it saves a lot of work because trying to drill that broken stud and keep it perfectly lined up between the threads sometimes can be very difficult. And if you bugger up the threads, well, then you might be pooched. So it says you can use the principle of dimensional upset to remove broken studs. Heat is applied to the end of the stud in the form of welding, causes dimensional upset on the broken stud. When heated, the stud cannot expand against the walls of the hole, but on cooling, it's free to contract in all directions, resulting in a dimensional upset that leaves the stud somewhat smaller in diameter, and the weld buildup can then be used to grip and remove the stud. I've never done this, I don't think, but I've always been able to weld a nut. So that was back when I was young and a lot steadier, and I could see what I was doing. Haven't done it in years, and I probably wouldn't be as successful as I was back in my day. Now we're moving on to objective 5. Describe the purpose and effects of preheat and post-heat. So preheating is a process done prior to welding and can be completed in 2 ways. A local preheat for tacking and small welds, and 2, a total preheat of material for slower cooling. So when required, preheating is included in the welding procedure. And I'm not too sure. Oh yeah, when you guys look in your modules, and I tell you it's got that chart, it says preheat, none required. If it is, it would say in your procedures, preheat, whatever, and that's what you have to do. Always got to follow procedure. So it says check the title block or the specification data block on the blueprint to see whether any preheat is required. The amount of preheat is usually specified as a minimum. When you use a local preheat, remember to spread the heat well away from the joint area so that the joint temperature is maintained while you weld. And here he's just doing like some kind of a nipple on there. It's not in my module, so a little different. So in your module, it says, I think it says figure 12 shows preheat being applied to a weld joint on a piping assembly. So they're just showing you some forms of preheat. Induction heat is also a good method for preheat. Let's see what induction heating looks like.
Ever torn off the protective foil under the cap of a new bottle of vitamins? Then you've seen firsthand a result of induction heating. Induction heating helps heat the foil so it adheres to the bottle. It's a common application used in commercial food and drug manufacturing as a way of applying safety seals, like those on vitamin and medicine bottles. Induction heating has been around for decades and is an efficient method for heating metal parts. Its traditional uses are many. Now, induction heating is being successfully used in industrial and construction applications involving welding, such as preheating before welding and stress relieving after welding. Let's look at what happens in induction heating. When electrical current flows through a conductor, it produces a magnetic field around the conductor. By alternating the current, the magnetic field is reversed. Placing a conductive material, like metal, in the alternating magnetic field causes the material to heat up. Here's why. Localized electrical currents called eddy currents are created within the metal. The metal has a certain amount of electrical resistance. The circulating eddy currents flow against the metal's resistance, causing it to heat up. Another contributing factor to heating is hysteresis. This occurs due to the material's resistance to the changing magnetic field. Eddy current heating provides significantly more heating than hysteresis. Now, let's look at a typical induction heating system for preheating or stress relieving. Induction heating uses a conductive cable, which can be wrapped around or placed on a metal part to be heated. Alternating current passes through the cable, creating a magnetic field in the part. The reversing magnetic field creates eddy currents and hysteresis in the part, which, as previously mentioned, creates heat. Induction heating is unique, as compared to most conventional heating processes used for preheating and stress relieving of welds. It is a non-contact method of quickly heating metal by inducing current in the part. Therefore, it does not rely on a heating element to touch the part to conduct heat, or a flame to impinge on the part. Essentially, the part becomes the heating element, and the highest temperature is generated and controlled in the part rather than the heating device. This process of heating makes induction highly efficient and extremely accurate.
Well, there you go. Now you have it. So here, this is another example of induction. Okay, so when I talk about induction, it's not the same as inductance. When on the machine, I tell you, you're doing short circuit metal transfer, set your inductance at 30 and forget about it, whatever. Uh, this is induction. So induction is the heating of materials without physical contact. Okay? Inductance, on the other hand, is it controls how many times your wire short circuits in a given amount of time. So don't get the two confused. And we've done this demo in the shop a few times, and guys, I could see the confusion on the faces of students, because as soon as we start talking about induction, they start thinking inductance. So I want you guys to sever that, so you know there's a difference in the two. Anybody not understand what I just said? Speak up. All right, let's see how this inductance works to heat up this solid bar. So there's no physical contact here whatsoever.
Okay, here we're heating 6 inches of a 1/2 inch bar. The induction heater is running on 220, and we're going to be pulling about, looks like 8 amps cold. We're going to see how long it takes to heat this up. Right now I have this on manual tuning, so I'm just, as the resonant frequency changes, I'm just manually tuning it up and down. About a minute to the point where it starts heating and the resonant frequency starts to change, and we have to track it. And then it very quickly, once it passes that point, raises in current. Now we're drawing about 25 amps, 26, and we're peaking above 800 volts peak to peak in this resonant tank circuit. So it's about a minute and 25 seconds to get it up to a bright orange, and we can keep going here and past the forging temperature and up to the point where it'd melt the bar in half, but we're not going to do that. Drop it back down above resonant frequency so the current drops, and it would actually hold the temperature there for quite well, for indefinitely, but there we go.
What do you think of that?
Works well.
So yeah, that in induction heating is heating of a material without physical contact. Okay, so now they're talking about purposes of preheating. So preheating prevents high stress or cracking. And it talks about metals with low ductility or are prone to cracking should always be preheated prior to tacking or welding, as this reduces the stress and the stress-induced cracking. And some examples of these metals are cast iron, high carbon steels, tool steels, medium carbon steels, and cast aluminum. So when you're working on some of these materials, preheat is normally required on thick sections. I think it says that in that paragraph or somewhere. Okay, so the thicker, you probably want to use preheat. And then it says preheating also reduces or prevents hardness. Small welds such as tacks or light seal passes to be made on thick, low carbon steel require preheat of about 150 to 250 degrees in order to prevent hardness, especially if the welds are to be machined later. Where higher carbon content or low alloy steel is used, the amount of preheat may have to be considerably higher in order to prevent the hardness and cracking. So preheating is also used to make arc striking easier. Where bronze and aluminum electrodes are to be used, preheat of approximately 100 degrees Fahrenheit makes striking the arc much easier. And the preheat also reduces the tendency for cold starts and the subsequent piling up of the weld metal at the starting point. And I think you guys have seen a fair bit of that. When you start off welding, you're starting off cold, and it kind of piles up right at the beginning. So the effects of preheating. Preheating slows the rate of cooling. It reduces cracking tendencies and enhances the mechanical properties, such as lowering the tensile strength. It reduces the residual hardness. It improves ductility, and it increases notch toughness. Then it says, because preheating slows the rate of cooling and enhances the mechanical properties, the tendency for cracking is reduced and often eliminated entirely. So our temperature for preheat usually range from approximately 100 to 400 degrees Fahrenheit, although can be as high as 800 degrees for alloy and higher carbon steels. Preheat should be avoided on austenitic stainless steels and some quenched and tempered alloys. And it says, if in doubt, follow the welding procedure to check with your welding supervisor. And then we'll talk about post-heating. Post-heating is the application of applying heat after the weld is completed. So back in the day when I used to work in the truck shop, I used to build these pickup plates. And the pickup plate is basically what they call a fifth wheel plate. And it's at the bottom of the front end of a trailer. And then the truck will back into what's called a kingpin. It sticks out of that plate. And the jaws on the truck, on the fifth wheel of the truck, locks onto that pin, and then they haul the trailer down the highway. Well, I used to build those plates. And that kingpin in there, I'd build the plate, I'd cut a hole in the plate, I'd set the kingpin into the hole, and then I would preheat the plate and the pin quite extensively with tiger torch. I'd get it to a certain temperature, and then I would start to weld around that kingpin. And then once I was done all my welding, I would take the torch and I'd heat the whole thing up again just to control the cooling. Otherwise, because that kingpin is of a harder material, I had to do the preheat and post-heat in order to remove any residual stresses on there. Otherwise, you can imagine a guy pulling that trailer down the highway and that pin cracks out and he loses the trailer. So, and I built hundreds of those plates. So it's really important to know when to do it and why to do it and all that stuff. So post-heating is the application of heat immediately after welding. Post-heating is different from post-weld heat treatment. In the post-weld heat treatment takes place at some point after welding and not right after the weld is completed. For example, stress relief is an example of post-weld heat treatment process that can take place days after the weld has cooled. So some of the purposes, the primary purpose is to slow the cooling rate, but there are a few others. Prevention of hydrogen-induced cracking. reduction of martensite formation in the weld and the heat affected zone, relief of residual stresses, and reduction of preheat temperature. And then the post heating temperatures. I just want to go on a little bit more in this other portion here. It says the prevention of hydrogen-induced cracking. Hydrogen-induced cracking usually occurs in the heat-affected zone, but can also be present in the weld nugget. Hydrogen-induced cold cracks can form in the metal up to several weeks after the weld is completed. Hydrogen is usually introduced into the weld nugget during the welding through the filler metal. As the molten puddle cools, the hydrogen is pushed to the heat-affected zone and to the surface of the weld. The hydrogen is not compressible, and as the metal cools, it contracts. It creates stress around this hydrogen. If the metal is a high alloy or higher carbon content, it's not ductile in nature and will crack. Post-heating the weld right after it is completed allows the hydrogen to migrate out of the metal and reduces the chance of hydrogen-induced cold cracking. Oh, what time we got? 10:02. I think we can, I think we'll finish this up tomorrow. How's that sound?
Sounds good.
Sounds good? All righty. So, where the hell am I? Post heating temperatures down here. Number 25, 26. There it goes. So I'll remember that. And you guys take a quick break and you can meet up with Barry, I guess. Are you meeting up with Barry or Tim?
Barry.
Well, there you go. So, yeah. And I'll see you guys in the morning. Don't be late. Because guys got a lot of work to do tomorrow.
Thanks, Doug.
Thanks, Doug.
Have a good night. Dobranic.
Have a good night.